today we start the lecture number 3 of phase equilibria course. So, just I will give you a recap of what we did in the last class. So, in the last lecture we learnt about the principles of enthalpy, which consists of internal energy and a PV term, and this enthalpy is basically the heat content of the materials, and enthalpy of, for example, liquids is higher than that of solids, or the enthalpy of gases is higher than the liquids. And then we talked about this free energy, and free energy is nothing but G is equal to H minus Ts, where S is the entropy. Entropy is a measure of randomness in the system. So, it is the relative competition between these two quantities as a function of temperature for most material system. The competition between enthalpy and entropy determines which phase will have lower free energy as compared to another. So, basically what happens is that as you increase the temperature, as temperature increases, so let us say you have phase 1 with free energy G1, phase 2 as free energy G2, and these G1 and G2 terms will include enthalpy and entropy terms. So enthalpy will increase as the temperature increases, entropy will also increase as the temperature increases, but since entropy term goes as negative, it is the competition between two will win. So, which will allow which will prevail. So, for instance, if G2 is less than G1 at certain temperature T1, then phase 1, phase 2 is more stable. So, you will find the system will drive towards having phase 2 as the stable phase. And then we came to concept of equilibrium. The concept of equilibrium was, so this is the free energy, and this is, let us say, atomic configuration. So, you can have free energy structure like this. So, you can see that there are local minimas. So, this is, for example, 1, this is 2, this is 3, and you can see that they have corresponding minimas, and you can see that state 3 has lowest free energy, but there are local minimas. So, these local minimas correspond to what we call as metastable phases. And this is the equilibrium phase. So, although metastable phases also have dg is equal to 0 at the minimum, if you provide sufficient time and energy, this will the atomic movement will happen in such a way, so that it goes from this to that and then this to this. So, this is the stable equilibrium phase if you allow sufficient time for the system to achieve equilibrium. So, this is what we discussed in the last lecture. In the today's lecture, we will talk about what makes a phase stable. So, questions that we will answer. What makes a phase stable, given that constraints are, so thermodynamic constraints are typically temperature, pressure and Ci. Ci is the composition of ith species, and how do various phases coexist. This we will see later on in more detail, but these are the questions that we need to answer in phase equilibrium. Topics related to, I would say, phase equilibrium. Okay. And then what happens when number of components change in a system, and then and so all of this requires a little bit thermodynamic framework. So that is what we will do in remaining lectures. So let us first look at the thermodynamic properties. There are two properties which we normally talk about. One is called as intensive properties. Intensive properties are those which are independent of size of the system. Size could be, for example, mass. And what are these properties? These properties are variables such as temperature and pressure. On the other hand, we have another thing called as extensive properties. Which are determined, whose magnitude depends upon the size of the system. So for example, so these are, you can say, dependent upon the size of the system. So examples are, so in this case example could be, for example, volume. Volume depends upon the size of the system. Internal energy U, or enthalpy H, entropy S, or free energy G, and all of these units you can see they are determined in so whatever the value is. So for example, you can have internal energy, you can have joule per mole. So they are basically, they are molar quantities. As a result, they are expressed as mole inverse. Okay, so they are basically expressed in the form of per unit mass. Of course, volume has its own unit in terms of meter cube or whatever. So most of these thermodynamic quantities are expressed in terms of mass of the system. Now let us look at the how the phase changes happen. So as you go, for example, let us say I go from temperature T1 to T2, okay, and this is the condition that T2 is greater than T1. Then the phase 1 has free energy, which is G1 to G1 prime. Okay, the free energy decreases as a function of temperature, and phase 2 is another one which has a free energy G2, which goes to G2 prime. Okay. Now in terms of thermodynamics, if at T1 G1 is smaller than G2, then phase 1 is stable, and if at T2 G1 is greater than G2, then phase, so I would say basically G1 prime is greater than G2 prime. So at T2 G1 prime is greater than G2 prime, then phase 2 is stable. Now phase transformation, if you, so when you go from phase 1 to phase 2, it may not be a continuous transformation. The transformation may happen may occur through series of steps which may involve formation of a few metastable phases on the way. So, you need to provide sufficient time. So, although thermodynamics tells you that phase 2 will be more stable if its free energy is lower at higher temperatures as compared to phase 1, the route to achieve phase 1 to phase 2 is not determined only by thermodynamics, but also by kinetics. So, phase transformation is basically determined by both thermodynamics and kinetics. So, we will not dwell into the kinetic aspects in this course. We will only determine with the existence of equilibrium phases at a given condition of thermodynamic constraints. So, we will only look at what kind of phases will exist if you define temperature, pressure and composition for a given system. So, let us just look at the thermodynamic aspects of it. Now, let us move to the next topic. The next topic is we first consider within this thermodynamic framework what happens in single component systems. Now, single component system basically what it means is that you have only one component. This could be pure iron or pure H2O. Okay. So, these could be the examples. So, basically in this case, since you have only one component, the thermodynamic variables are temperature and pressure. These are the two important variables that we have, and we will see some example of this. So, let us see. So, basically what we do is that we want to predict the phase stability as a function of temperature and pressure for single component system. So, let us first look at how the free energy varies as a function of temperature. Now, in this regard, first we would like to define the specific heat. Okay. Specific heat is now specific heat is something which is easily measured. It is a measurable quantity, and it is known for most substance. So, when you plot specific heat as a function of temperature T and then specific heat. So, the unit of this will be joule per mole per Kelvin. Okay. So, a specific heat of most substance goes as something like that. Okay. So, start from 0. This is the variation of specific heat will be. And what is a specific heat? A specific heat is basically amount of heat that is needed to raise the temperature of a substance or temperature of 1 gram or unit mass of a material by 1 Kelvin. So, basically you are all aware of what is Cp. Cp is the specific heat at constant pressure. So, amount of heat needed to raise temperature by 1 Kelvin of unit mass of a substance or material. Okay. So, at constant pressure Cp is defined as del H by del T at constant pressure. So, this is the expression that you have for this, comes from basic thermodynamics. Now, another thing that we need to note is enthalpy of a pure substance H is equal to 0 at 298 Kelvin. This is what is taken as a reference level. If H is 0 at 298 Kelvin for a pure material taken as a reference level, then all you need to do is that you need to integrate. If you want to find out the variation of H as a function of temperature, you need to integrate Cp. So, for finding enthalpy, the H will become, you need to go from 298 to temperature, and then you can do Cp dt. And when we plot this as a function of temperature, so this is H, this is T. So, H is basically joule per, let us say, mole, and this is, let us say, 0 Kelvin, and the behavior of this is something like this. So, at 298 Kelvin, H is 0, and the slope of this is basically, you can say, is Cp. Okay. So, this is what is about enthalpy. Now, let us look at the variation of entropy. Now, we know that Cp, from the basic, you need to know this much of basic thermodynamics, Cp divided by T is del S divided by del T at constant pressure, because you know del S is equal to dq by ds is equal to dq by T, and Q, for all practical purposes, if PV term is small, you can take Q as H. So, basically this will become the same as what we saw. So, basically what you have done is you have replaced dH by dq, ignoring the PV term. So, as a result, your here you had, so this will become Cp is equal to Tds divided by dt. Tds is nothing but dq, dq is nothing but dH. So, we are following the same definition, right. So, since at, now by definition, at 0 Kelvin S is equal to 0. So, then if you just integrate this expression, the above equation, S will become integrated Cp over T dt integrated from 0 Kelvin to T, some temperature T. So, this is the expression for entropy that you will obtain from the basic thermodynamic equation, and if you plot this, the plot will look something like that. So, this is 0 0 T in Kelvin, we have entropy, okay, and okay. So, this will follow a behavior which is something like this, okay. So, this is the variation of entropy. So, entropy increases as the temperature increases. So, you can see both of them. The enthalpy also increases as a function of temperature, and the entropy also increases as a function of temperature, but in the free energy equation, G is equal to minus H minus Ts, the enthalpy increases and this term will decrease because S is also increasing as a function of temperature. So, now we know that G is equal to H minus Ts. Expand upon it further, dg, if you look at the incremental change, then this becomes dh minus TdS minus S. Differential form will be this, and we know that H is equal to U plus PV. If you replace this, then dg will become du plus PdV plus VdP minus TdS minus S dt. Now, for a system, so this is the expression that you get. So, now for a system with fixed mass and composition, we write du to be equal to dq minus dw, and this is basically TdS, because dq is equal to TdS, or you can say ds is equal to dq by T by definition of second law. So, TdS minus of PdV, and we take this dw is equal to PdV for a closed system. So, you can say W is equal to PV. Okay. Now, if that is the case, then dg becomes, if you replace this, it becomes TdS minus PdV plus PdV plus VdP minus TdS minus S dt. So, we cancel this, and what we obtain at the end is dg to be equal to VdP minus S dt. This is the basic thermodynamic equation that we have. So, at constant pressure, of course, dP is equal to 0, and hence dg is equal to minus S dt, or you can write alternatively del G by del T at constant pressure to be equal to minus S. So, this is the variation of free energy as a function of temperature, and you see that this is minus S. So, free energy, since as the temperature increases, the entropy increases, the free energy will decrease as a function of temperature. So, this is a very important relation that you obtain, decrease of free energy as a function of temperature at constant pressure. Okay. So, now let us plot, let us make a plot. So, this is 0 and this is T at Kelvin. So, we are going to plot both H and G. The H for a given phase will vary like this. So, this is the variation of H, and the slope of this of course will be nothing but Cp, and this is, you can say 298 Kelvin when H is equal to 0 at 298 Kelvin, and the free energy goes as, if you now as like this, and the difference between these two is nothing but, you can say Ts. This is the difference, the Ts. So, this plot that we have shown is of G, and the slope of this is nothing but, what will be the slope? It will be equal to minus S, as we wrote in the previous slide. So, you can see that as a function of temperature, although the enthalpy, so here you can write H comma G. So, as a function of temperature the enthalpy increases, but because of increasing Ts term the free energy decreases as a function of temperature and the slope is minus S. So, let us just look at an example of liquid to solid. So, I again make a plot in this fashion. And we will plot both. So, let us say if I first draw the free energy for a solid phase, free energy for a solid phase would be like this. So, this is 298 Kelvin, this is H for solid, all right. And then free energy for liquid would be enthalpy. So, this is enthalpy of solid and enthalpy of liquid would be higher than that of solid. So, if I now plot the enthalpy of liquid, enthalpy of liquid would go in a fairly similar fashion like this, and the free energy of two phases. So, for the first phase the free energy would be so if I take the free energy it would be like this, okay. And for the second phase the term would be like this. So, now if I look at it in a different, so what I have drawn here is this is free energy of let us say the solid phase G solid, and this is G liquid, and here it is H liquid, okay. Now, what we see from this plot is, first let us look at the free energy. What happens at the free energy is that free energy of both solid and liquid phases decrease as a function of temperature. However, we see that at this particular temperature, let us say this particular temperature is some transition temperature, let us say in this case Tm, which is the melting point. We see that below the melting point the free energy of solid phase is lower, but above the melting point free energy of liquid phase is lower, which means solid is stable in this regime. So, we can say in this regime Gs is lower than Gl. So, we can say solid stable. In this regime Gl is lower than Gs, we can say this is liquid stable regime. And what happens, corresponding changes in the entropy? The entropy on the other hand, the enthalpy, you can see that at this temperature the overall entropy curve follows something like that. It follows in the fashion like this up to this point, then at melting point there is sudden jump and then it continues. So, this is what is the overall change in the enthalpy, and you can see at Tm at this point there is no change in temperature, all the heat that is added. So, this is the heat that is added, okay. You can see this is heat added. This is basically the heat that is added for solid to convert into liquid, all right, and this is basically the latent heat as we call it. So, when this heat is added, the bonds are broken, the solid is converted into liquid without raising the temperature of the material. So, temperature of the material does not raise at this point, it remains at Tm, which is called as the melting point. And free energy curve on the other hand, if you want to plot in a different way, the free energy curve up to this point, the free energy of the system continues like this, and after this point the free energy of system continues like. So, this is the overall free energy of the system. First is it follows the track of solid, and at melting point it starts following the track of liquid phase. So, this is what we have discussed in this lecture as to how the phase stability, how the phase formation happens, and at what as a function of temperature, how is the stability of these two phases governed with respect to corresponding changes in the free energy and the enthalpy. So, we will stop here. In the next lecture we will further discuss this, and we will also discuss some more concepts related to change in the pressure of the system. Thank you.